How's it going? I hope everyone's doing well today and that you enjoyed the longer weekend. All right, so first thing, were there any questions on homework that we would like to go over? No questions on homework? Okay. So, going back to what we talked about on Tuesday last week, or Thursday, sorry. Today's Tuesday. Um, this is that data set I'd written down before, ages of stats students in an evening stats class. And we have 20 data values, and we already determined, based on what we saw before, that the maximum is 45, the minimum is 18. We plan to use 6 classes. And so we said, okay, our width would be the maximum value minus the minimum value divided by the number of classes. That's our general formula for class width. And then we subtract and then divide, and we came up with 4.5. Now, we can't use a decimal class width. We need a whole number. And so we always take whatever result we get there and we round that up to the next whole number. Even if this had been 4.1, we'd round it up to 5, because if we make the width any smaller, then we won't get all of our data in the 6 classes. But if we make our width larger, that means that last class will contain the last piece of data, the highest data value, and as a result, there will be a little bit more space in that last class beyond the highest data value, but will contain everything in an equally width, classes with equal width, I guess. Yeah. So we have this information, and now the goal is to create our classes, which is where we stopped before. Let's see if I can keep that handy. All right. And I don't think I need so much horizontal space because we just need 2 more columns. This will be frequency and relative frequency. Okay. Now, we had said our width was 5. Okay. Now where we start our classes, first class starts at the lowest data value, the minimum data value, which is 18. Okay. 18 is our minimum, so class 1 will start at 18. And now from here, our width is 5. Now, we have to be careful about how we apply the width. We actually add the 5 to 18 to get 23, and that means the second class will start at 23. Okay. Now our class, when we call it a class of data values, this is actually a range of values. And so we know our first class starts at 18, and then if we add our width 5, the second one starts at 23. If the second one starts at 23, where does the first one end? What value would the first class end at? 22. Good. Okay. So that means our first class will be from 18 to 22. So that'll include all the 18 to 22 year olds in this statistics course. Now we look at that pair of numbers and we say, okay, how does that class width of 5? Because we look at those two numbers, and if we were to subtract, like 22 minus 18, they're only 4 units apart. But the reason we say the class width is 5 is if we look at all the different ages that are present in that particular class. 18, 19, 20, 21, and 22. That's 5 different age values present in that class. Even though there's a distance of 4 from the first to the last, if we include the first and the last number, that means there's 5 different data values there, which is why we call it class width 5. It's a little strange when we look at it that way, but that's actually how it's regarded. Okay, once we get these 3 values down, like the first class and then and this one here, we know that we can just keep adding 5 to create additional classes. So this second class then is 23 to 27. We just add 5 there. What would be the third class? What numbers would the third class start and end at? $28, and it would go to will be the top number. And 32, right. So we add 5, we add 5. Okay. And now we keep going. So from 28, I'll have to draw this down a little bit more. Add 5, so we get 33. Add 5, we get 37. That's our fourth class. Our fifth one, 38. The sixth one, to 42. And then the sixth and last one would start at 43 and go to 47. Okay. Are there any questions on how we created those classes? All right. So we start at the minimum value. We utilize the fact that our class width is 5. We add 5 here. to get 23. Then we backtrack to get where the first class ends, which is at 22. Because we just say, okay, well, this one starts at 23, then the previous one must end at 22, the one right before it. And so from there, we just keep adding 5 vertically to get from each term to the next. And that's a good point, Aileen. We said our maximum value is 45, so this last class does go to 47. Yeah. And the reason for that is because we want all of our classes to be the same width. Same width means each one has the same distance from first to last. Okay. In a proper grouping, we want all of our classes to have the same width. And because of that, there's going to be a little bit of space in our last class where it goes a little bit beyond where our maximum value is. So even though 45 is our maximum value, technically our final class goes from 43 to 47. Okay, and it's just one of those things. We can't really effectively, we know it's not going to go anywhere past 45, but this is the best we can do with the data. Now, is there a grouping scenario where we start at 18 and end at 45? Probably. It's not a simple thing to think about, though, necessarily. Because if we look at our our class width, our calculation here, where we did 45 minus 18 over 6 is 27 divided by 6. I guess in order for it to work out properly, we would have to have something that's a factor of 27. So if we had 3 classes, which we wouldn't want 3 classes, or we could have done 9 classes, that might have worked better, and have the last group end at 45. No, that wouldn't have worked either. I'm sorry. There's a pattern to do that, but we don't really need to spend a lot of time focusing on that. Is ultimately what happens. And so, even though we go a little bit past our 45 or max value, it's okay, basically. Okay, and now the kind of tedious part of this is now figuring out how many of each of these values from our list of 20 data values fit into each of these classes. One way we can do this is with taking a tally of values. For instance, our first column, 18, 21, 37, 18, 18, 21, 37, and 18. We just make a mark in each of those classes where those appear. Our second column, 20, 18, 18, and 32. So 20, 18, 18, and 32. Then we have 19, 25, 21, 45. 19, 25, 21, 45. 23, 20, 27, 19. Okay. Last column, 19, 29, 20, and 18. So 19, 29, 20, and 18. So we have 5, 10, and then 3 more, so 13 as our frequency in our 18 to 22 class, which is kind of our what we call our traditional college age. Next class, 23 to 27, 3 students. 28 to 32, 2 students. And then 1 here. We actually have 0 in this group, 38 to 42. And then 1 at the higher end, 43 to 47. Are there any questions on how we created that frequency table? At least that column. Okay. Now that we have our data arranged in a nice set of groups, first of all, we double check, make sure this adds up to 20. So 13, 16, 17, 18, 19, 20. And it's always nice to double check to make sure we've counted 20 different values here. Next, we look at our relative frequency. How are we going to calculate the relative frequency for this first class? Do you remember what we did there? No one? Oh, yes, divide frequency by total. So we would take our frequency 13 and then divide it by 20. And so that'll give us 0.65. And then we'll repeat that for each of our frequencies. So 3 over 20 is 0.15. 2 over 20 is 0.10. 1 over 20 is 0.05. That one's 0. And then 1 over 20 is still 0.05. And again, this last column we expect to end up adding up to 10 or very close to it if we've approximated. And in this case, we didn't have to approximate, so we should have exactly 1 when we add these together, or 100% if we use percentages instead of decimals. 65 and 15 is 80, and then 10 is 90, 95, 100, so 1.00. Okay. Now, so that's our grouped frequency distribution. The most complicated part of this, I think, is setting up the classes on the on our test, our first test, which is again, oh gosh, I didn't post the schedule. I'm sorry about that. Let's see, we're in chapter 2 still, so we're nowhere near a test yet, but it'll be maybe 2 or 3 weeks from now. We'll see. So I wouldn't say nowhere near, but you know, it's coming down the road, but not immediately, thankfully. Anyway, on that first test, I actually will give you the classes, and you just have to fill in the frequency and the relative frequency, and you can take a tally if you like as well. Now, one of the things that we're talking about displays and how we would display different types of quantitative data in this section 2.2. One of the things that might make this easier is what's called a stem and leaf chart. Okay. And in a stem and leaf chart, the idea is that data values are grouped by some common term. Okay. Now, what we mean by some common term is that we may see that in our data set, a lot of the in case of ages, a lot of the tens digits are repeating. Like we have a lot of people in their teens, a lot in their 20s, a lot in their 30s, not so many in the 30s, and then not so many in the 40s. But there's some commonality there that we can group them by. If we talk about prices of goods, then we can group them by the dollar amount and then order them by the cents amount. Ages, we group them by the decade, but then order them by the individual year. And there's different ways that we can do that. It just depends on what level of commonality our values have. If we have a wide range of numbers, it's a little bit harder to do a stem and leaf chart, but it's still possible. Let me show you, for example, this same data set that we've been working with here. All of our values we know are between 18 and 45. Okay, so our stems that we're going to use are 1, 2, 3, and 4. And the idea there is that this represents people in their teens, people in their 20s, people in their 30s, people in their 40s. Now we only have one person in their 40s in this data set, and they were 45 years old. So we put 4 and a 5. So this is 45. We have our stem, we have our leaf. Next, if we look at our data, we had two people that were in their 30s, a 32-year-old and a 37-year-old. So 32 would be first, and 37 would be second. So 32, 37. Now, we have a number of people in their 20s. Let me see if I can arrange this. Let's see, we have, overall, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 people in this data set that are in their 20s. Which one would be first? Or what would be the first terms that we use for the leaves for the 20-year-olds? 0? Mm-hmm. Now, one of the things specific to the stem and leaf chart is that because we have 3 different people in this group, or in this data, that are exactly 20 years old, we'll actually write down the 0 3 times. And that didn't really come up before in the previous examples, but that's what we can use there. And then we go through and look at 21. 1, 2, just 2 21-year-olds. 22. We may not have had any 22. So next would be 23. That'd be 1, 23. And then we look 24, 25, 26, and so on. We have 125-year-old, I believe, is next. So that's a 5 that we'll write down. No 26-year-old. Then we have 127-year-old and then 129-year-old. Okay? And so again, this is 20, 20, 20, 21, 21, 23, 25, 27, and 29. Then we'll repeat this for the the ones in their teens, which is basically just the 18 and the 19-year-olds. We had 1, 2, 3, 4, 5 people, 18. We separate these by commas, as you can see. And then 19, 1, 2, 3. Okay. Now again, it's worth double checking that this adds up to 20 total people. So 8, 17, 18, 19, 20. Okay. But now we look at this group frequency distribution. Once we have our stem and leaf chart, like we have here, basically the stem and leaf, what it does, not only do we group these values by basically tens in this case, it's not quite the same as breaking up in the classes, but in a way it's similar. But it also forces us to put the values in order. And you'll notice that in each of these cases we arrange them in order from low to high per stem. And so from here, and also I tried to make evenly spaced, columns, quote unquote, where we can actually see that there's a few more in there, one more person in their 20s than there are in their teens. So, how does this help us create a class frequency distribution or group frequency distribution such as this one? Well, now if we say, okay, our first class goes from 18 to 22, it's much easier to count. 18s, 20s, 18, 19, 20, 21. There aren't any 22s, but we can easily count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 individuals that fit in that range. Okay. So, knowing that that's 13 people, we then look at 23 to 27, which is 1, 2, 3. And you can see we wrote down a 3 here. 28 to 32 would be our 29 and our 32-year-olds, so 2 people. 33 to 37, 1 person. 38 to 42 would be 0, and then 43 to 47 would be 1. And it perfectly matches with the frequencies that we got already, but looking at it in this table, the stem and leaf chart that we created, it makes it a lot easier to count those without having to go through and make it a tally chart. Now, the stem and leaf is only useful, I think, it's the most useful, I would say, when we have less than like 100 data values and there's not a huge amount of variety in the numbers. So when we talk about ages, that's a good way to use it. If we look at what else can we use? If we use let me show you some different data. This will be prices of candy in a store So let me just kind of make up 10 values here that we can utilize. So we might have one that's 79 cents, $1.29, $1.39, 59 cents, $1.19, because everything ends at 9 apparently. I'm just making this up as I go, but let's see, 209, 259, 79, 089, and 129 again. Okay. In this case, when we're dealing with decimal values, and we want to try to think of how can we group these together for a stem and leaf chart. Well, in this case, I would say we could use the dollar amounts as our stems and then the cents as our leaves. So we could say for our stem, we have some that are in the $2 range, some that are in the $1 range, and some that are less than $1. In that case, what do we use as the stem? Yeah, we'd still use 0 there. And it helps that I think that I wrote 0 here, but if we just said something costs 89 cents, the 0 would be implied. Okay. And then for our leaves, we would write 59, 79, and 89, for instance. Because we have one that's 59 cents, one that's 79, and one that's 89. Here, here, and here. What would our leaves be for the one stem? Yeah, 19 would be first, but then in order, we have a 29 after that, but in fact we have two 29s, so we have to make sure we write it twice. Good. And then 39 and 79. And then at $2, let's see, we have 209 and then 259. Now you could write 09 or you can just write 9. Either way is fine in that case. It's $2.09, $2.59. Okay. Does that make sense? I hope. All right. Now, let's go back to our age data. And we said, and this is, I'll flip this back over. You know, we ended up with this table, class frequency and relative frequency. So next thing I would like to do is make a histogram for our class data. Now we talked about histograms already in the first part of section 2.2 last week, but it's a little bit different when we have grouped data like we have here versus when we're looking at ungrouped data. which I don't have the page anymore handy. With our grouped data, the way that we label our horizontal axis does change. And this is what's frequently confusing for a lot of students. So it's one thing I want you to watch out for. So we're going to create a histogram. Okay. Let's go ahead and use relative frequency here on the vertical axis. For our title, we're going to put ages of evening statistics students. And on the bottom here, I'm going to make some marks. We have 6 classes, so I'm actually going to make 7 marks here. Okay. Always make one more mark horizontally, then we have classes. Okay. Now, the way that we label this is according to the lower limit of each of our classes. Okay? So we have 18, 23, 28, 33, 38, and 43. Okay. Our first class goes from 18 to 22, and so we'll draw that bar from here. It starts at 18 and stops before you get to 23, and so we'll draw its height accordingly between these two marks. Our next class starts at 23, goes to 27. So here we'll actually start at 23, but the bar will end here at 28 where the next one starts. It's a little bit weird, actually. This is how we do it, though. There's a lot of questions, I'm sure. The people that create statistics, some things don't always make perfect sense, unfortunately. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Actually need one more mark to make 13, because that'll be 65%, 13 times 5. And we can just count by 5s here. Okay. Now, you may have noticed we didn't make a mark here at the end. Okay, I said we needed 7 marks, but then we only wrote down the 6 lower limits. What would be the next number if we keep going in the same progression? .48. Now the number 48 has nothing to do with anything basically in our data set. I mean, we already know our highest data value is at 45, but we need to go ahead and make one more mark, basically where, if we did have another class, where would it begin? And that would be at 48. We just continue the same pattern because we know our first class has to be between the first two numbers. 18 to 22 has a relative frequency of 65.65. Our next group 23 to 27 goes up to 15% or 0.15. After that, we have 10% between 28 and 32. Starting at 33, we have 5%. 0 from 38 to 42. And then our last group, starting at 43, has a relative frequency of 5%. And so that would be our histogram in this case. It may seem a little bit confusing when we first look at it. It's actually easier than how I've seen other textbooks do it, but the point is they're kind of flexible here. But let's try to stick with what the book is telling us in this case, just for consistency's sake. Honestly, I like this better than what I've seen from other textbooks, so and maybe that's something that's changed over the years as far as what's generally accepted as practice here among statisticians. But yeah, for our grouped classes, we basically state where each class starts. Like this one starts at 18, this next one starts at 23, this next one starts at 28, the following one starts at 33, then at 38, and then finally 43, and the last one would be at 48, except there's no more groups after that, so that's where the last one stops, basically. Okay. Now, all the stuff that we're doing here with working with this one data set, you can imagine the first part, or I guess technically the middle part of our exam, the one that deals with chapter 2, will cover all these same concepts working with a single data set. So I'll give you a data set, I'll have you make a stem and leaf chart, then I'll have you fill in a frequency distribution table, and then I'll have you make a histogram based on that. Okay? And there's other things that we'll talk about that go along with that same thing, but we haven't talked about it in chapter 2 yet. Okay. Any questions, though? Now, the last thing that we're interested in this section is how do we identify the shape of a distribution as it refers to a histogram specifically. So here's our primary shapes that we like to look at, or like to teach at least. Let me get it where there's not a lot of glare, hopefully. The answer is no, not possible. Oh, there, that's a little bit better. So there's different types of distributions. This is called a uniform distribution because each of the bars has, in this case, in this picture, they have the same height, but even if something is considered uniform, it could be slight variations from one height to another. So if everything's approximately the same height straight across, we could still call it a uniform distribution. So we don't have to go too much further into that. I've had algebra courses that I've taught where the grade distribution is roughly uniform as far as the A's, the B's, the C's, the D's, and the F's. Bell-shaped or symmetric distribution. The signature feature here is that it's highest in the middle, and it kind of tapers off to both sides. Okay, highest in the middle, and then decreasing heights as we go in both directions from there. Kind of like how we would see the shape of a bell, kind of our standard shape of a bell. Think about maybe the Liberty Bell, for instance. Starts high in the middle and then kind of curves off to both sides from there. Okay, so we call that a bell-shaped distribution. And anytime we have something that's standardized or normalized, we frequently use that bell-shaped distribution to work with that. And that's something that we'll work with a lot more in the latter portion of the class when we get our standard normal distributions that we start looking at. We also have data that is skewed right. Now, we call this skewed right, and this one's skewed left. So we think of, okay, the middle, or the highest point is actually on the left, even though we call it skewed right. The reason we call it skewed right is that this would be considered a bell-shaped graph if not for this kind of tail that's going off to the right-hand side, where we have some different extra values on the higher side that we don't have on the lower side. So we say it's skewed right is kind of a bell shape, but with a longer right tail. We would call that. Okay. Whereas with a skewed left graph, this would be almost bell shape right here, except we have a longer left tail. Okay. So really, in these two types of distributions, it's which side has the longer tail. That's the direct direction that it's skewed. Frequently, this is what I see skewed left. That would be like a lot of my stats grade distributions, where we have a lot of A, B, and C's, but then fewer D's and F's compared to my algebra class. So, anyway, in general, not always. All right, I really hate to have that one. All right, so that's our four major types of distributions. There's others that we could have. Some books talk about like a U-shaped distribution where it's higher on the ends and lower in the middle, or a J-shaped distribution where it's higher on one side, there's a decrease, and then a slight rise on the other end. Basically like the letters are shaped, but they're less common. With sufficient data, then we should reasonably expect to see one of these four. Okay, unless the data we get is very distinct, I guess we could say. We should expect something like this. Bell-shaped is great because anytime we talk about if we have a sufficient number of values, then people's height tends to be bell-shaped, where we have a lot of people kind of near the average height, but fewer that are really tall and fewer that are really short, relatively speaking. So that's things like that. We can see that appear. Any kind of standardized testing that you've done are basically bell-shaped distribution. If you took any AP tests in high school, those are bell-shaped. As far as how they assign grades, where it was a score 1 through 5, whereas 3 was the most common score given, which is right in the middle. Then we have fewer 4s and then even fewer 5s above that, and likewise fewer 2s and then fewer 1s below that. We'll talk about the bell-shaped distribution a lot more later, so we don't have to go into a whole lot right now. So looking at these four designations that we've used, and we go back to our histogram that we made for our ages in the evening stats class, which of those four do you think would work best to describe what's happening here? doesn't exactly fit perfectly any one of these, but there's one that predominantly follows more than the others. The characteristics of. Right skewed? Yeah. Now, right skewed tends to have, like, an up and a down and then a tail. In this case, we don't really have the lower bit. We just have the high bit, and then it just decreases as it goes to the right. And so, yeah, that would be the closest approximation we could call this would be right skewed or skewed right. Yeah, it just depends. If we look at the stem and leaf that we created for this data, in the stem and leaf, this kind of groups it by tens. If we think of these as classes, the 10s, the 20s, the 30s, and the 40s. And in this, it looks a little bit more right skewed, because now we have the highest bit in the middle, a little bit lower to the left, and then it kind of has a shorter tail to the right. Although 4 classes doesn't really greatly distinguish what's going on here. But we can think about the list of numbers as kind of a bar if we look at it sideways like we're doing here. So tall, taller, short, and then shorter. So in both cases, though, we would ultimately say right skewed. Okay. So as you imagine, in this section, as far as the homework that I'll give, going beyond what we've talked about here, well, not even beyond what we talked about here, but basing on what we've talked about here, you're going to be given like a list of data values or data set, basically. What I'll do is have you create the frequency distribution and the relative frequency, just all in the same table, and create histogram for those. And we'll also ask about the shape of the distribution. Okay. Now these, they will have you create the classes yourself. Although I said on the test that I'll actually give you the classes. But whenever we get to our first project, we'll certainly have to create the classes ourselves. Just in a test situation, I want you to be able to not panic about that. Plus, it makes it a little bit easier for me if all the classes are the same for everyone, as far as grading goes. But that's more on the selfish side of things. But I think for y'all overall, it'll be helpful to do that. So, for instance, if we look at this problem 29, we have a whole lot of data here. What I'll probably also have you do is create like a stem and leaf chart. Maybe not 29 though. That's an awful lot of data. Well, that's not terrible, but I guess it's 50. I don't want you to have to do 50. That's a lot. Some of these are even worse if you look at them as far as the amount of data they provide. Trying to figure out the question for this. Sorry, this looks like a reasonable amount of data here. This is the grams of fat in a McDonald's breakfast, based on what they present on their webpage. And we can very easily make a stem and leaf out of that, and we can create a group distribution and that worked pretty well. So I'll probably have y'all do that problem, and then with that data, do all those things I talked about. Maybe one more I would like for y'all to do. I'll look at it before we wrap things up. In section 2.3, section 2.3 is on additional displays of quantitative data, which is a little hard for you to see there, sorry. And they discuss things like this, which is a line graph, or sometimes we call it a frequency polygon. And the idea is that as this is the 5-year rate of return on an investment, and then the frequency that those occurred. Basically, we can see how things change from one level to the next, or from one instance to the next. It's not really a time series graph, but it really just it is a frequency polygon. But basically, we can see where differences exist in data values, where it changes from higher to lower, for instance. Now, this is a time series graph here, and this is a pretty common one, where we just list out the year on the bottom, and we see how some particular thing changes from one year to the next. This is talking about the Partisan Conflict Index in the United States federal government, and how let me see. It tracks the degree of political disagreement among U.S. politicians and the federal government, found by the frequency of newspaper articles reporting disagreement in a given month. This was 2014, so I imagine by 2020 we're up here somewhere. I don't know. Just guessing. Anyway, but that's the idea of a time series plot, is that, how things change over time. Okay, and sometimes we'll see them like two different things in the same graph. This is another time series plot, because we're still talking about the different years on the bottom, but we're comparing unemployment rate to inflation rate, and see if there's any kind of connection between the two. There's other tools that we have for measuring the connection between two different variables, and we'll talk about that later. I think it's in chapter 4, I believe. But for now, this is one tool that we have, and we can kind of see that it may not be a whole lot of connection there. Because we have the inflation rate, which is kind of all over the, bouncing up and down, and then unemployment doesn't really, I don't know, it's kind of an inverse relationship if we look at it, but not completely. But we can easily compare the two just by looking at this one graph, which is one thing that we're not going to go into these things I'm talking about in section 2.3, but I just wanted to mention them so that you could see them at least. The other thing I want to talk about today is section 2.4, and this is on the graphical misrepresentation of data. And let me whoa. The zoom function on this is intense. Anyway, let's leave it like that. So, a home security company located in Minneapolis, Minnesota, develops a summer ad campaign with the slogan, "When you leave for vacation, burglars leave for work." According to the city of Minneapolis, roughly 20% of home burglaries occur during the peak vacation months of July and August. The advertisement contains the graphic shown in Figure 20. Explain what is wrong with this graphic. Okay. Basically, we're showing how this company is misrepresenting, the frequency of burglaries in Minneapolis, specifically during these peak travel months, July and August. So July and August we have 20%. Other months we have 8%. Okay. Now, there's a couple of issues here. Theoretically, all 12 months are represented here. July and August are represented here, and every other month is represented here. But the problem is, the other 10 months besides July and August, none of these months are listed individually. Okay? That's part of the problem right there, is none of the months are listed individually. July and August have been combined together to make 20%. And the other months basically average out to 8% each, and that's what they've listed here. So, functionally, we see that the two numbers they've given us, if we think of them as representing all 12 months, these 2 months represent 20%, so maybe 10% between them on average, and the other months are just 8% each on average. What they're trying to do, though, is scare the potential customers into getting a security system by saying, we have a massive spike in burglaries in July and August that we just don't see in other months. And so they publish something like this prior to that, maybe at the beginning of the summer, so they can sell a lot more security systems. Not saying having a security system is bad, but we shouldn't be pressured into it by bad data. So July and August, maybe 10% each. Other months, 8%. And in fact, on the next page, they show us the true data. Now, we do see that it peaks in July at 11%. August is actually just 9% and lower than September and October. September and October are at 10%. Now, Minneapolis, being a part of Minnesota where the temperature is consistently low in the winter, we get a massive drop as winter comes on strong in February, which is understandable. Crime, I guess, is less likely to happen when you're freezing to death. Anyway, maybe not, but apparently in Minneapolis that's the case. But basically warmer weather, more activity; colder weather, less activity. That's what they're basing on here. So it is true, to a sense, that the burglaries do increase in the summer, but the company is actually overrepresenting it by presenting and misleading data. Okay, and trying to influence potential customers based on that. So part of being educated as statisticians, or just being able to use statistics in our everyday life, part of it is being able to recognize when data does not tell the full story or is being misrepresented. Okay. That's why it's important to have context for our data. That's why it's important to recognize that all the data they give us should add up to 100%. You're looking at this last graph, it only adds up to 28%. If we just think of those as two categories, well, that's 28. That means something's happened here where they're misleading us, because we should have 100%. In reality, they've added 2 months together and averaged the other 10 months. Okay, which is completely non-representative of what's happening here. While it is true, their claim that the burglaries do increase in the summer, it's just not by the 250% that we see here. Okay, it's not that massive of a gain. there's a gain, but it's not like a crazy spike. Okay. All right. Now, oh, sorry. Let me look at this example first. Example 2 covers the misrepresentation of data by manipulating the vertical scale. And we see, okay, highest marginal income tax rate. This is the the additional tax levied on people in higher tax brackets. We see in 2012, it was the bar was this high, and then in 2013, the bar is now much higher. So without looking at the values on the graph, you just look at these two things. Hey, this bar in 2013 is like 3 times as tall as the bar in 2012. So it looks like we have a massive spike in tax on the highest income bracket from one year to the next. And while it's true there was an increase from 2012 to 2013, at the same time, it wasn't as drastic as is being represented in this particular graph. We look down further. This is the actual data. Okay? And the reason that they look different is we look in this first graph, our data starts counting at 33. We don't start at 0, we start at 33%. And we just look at the difference from there. This is 35%. This is almost 40%, basically. And so, looking down here where we properly start at 0, oh, sorry, you can't quite see that. Where we properly start at 0, we see that the bars are actually much closer together, and there hasn't been as big of an increase as might have been, being tried to present here. And so, again, that's one of the tools that we see different people, different companies utilizing in order to swing opinion a specific way. Okay, so it's important that we pay attention to the vertical scale. Like in a proper statistical graph, we always start at 0, and we have equally distant points going up from there. Now, because we may have data that their values are pretty close together, but we still want to be able to show the differences between them. I mean, we can certainly want to show the difference between one year and the next, but we don't want to start at 33. We still have to start at 0, technically. So in this example, it's really the same thing, and this talks about the number that are in poverty, which is absolutely an increasing problem. We can tell that by the scale being presented here. Even though the scale actually starts at 30,000, it's still a problem. But it looks like, the way that we represent it, we see that, and these are equally distanced, which is nice. When we say equally distanced, that means we're counting by the same number from each mark to the next. So 5,000, 5,000, 5,000, 5,000. So that's good. But we still start at 3,000 or 30,000. Okay? And again, the other issue is that this is measured in thousands, so this is actually 30 million, not 30,000. So we want to be mindful of that also, is that in order to more easily express these numbers, we may say something is measured by the thousands. So we have 30,000 times 1,000, which is actually 30 million. Okay, and then an alternative to that still lets us show the relative differences from one year to the next is we start at 0, but then we indicate that there's a gap there by putting kind of this zigzag shape right here. Hopefully y'all can see that pretty well. we have the zigzag shape. That means that, okay, we started at 0, but then we skipped a bunch because we want to get to, everything here has higher than 30,000. And everything's in the 30,000 to 50,000 range, or 30 million to 50 million range. So let's get that out of the way, and now we can look better at how these numbers change from one year to the next, as is being represented on the horizontal axis. So now this is just raw numbers, which is, it does tell a story. But maybe a more significant story is if we look at the relative frequency versus the total number. It's a tragedy either way. We're talking about poverty. But when we look at the relative number, that takes into account how population changes as well. Both of them are. Both of them tell an important story, actually. But I'm going to have to zoom back out for that, sorry. The bottom of the page is hard to get to here, apparently. Maybe I can do this, sorry. And zoom. A little bit better. I had it. Lost it. Okay. So in this example, it's actually the same data, but now measured against the population as a whole. Now we can see it's still increasing and still relatively the same shape, actually. But there's a little bit of differences because, well, not a huge difference, to be honest. We still see a big spike right in here. For whatever reason, we don't. I'm not sure why, but as a proportion, we can see that it really peaks here and then kind of hovers there for a while. And the other thing that it mentions here is that instead of using a bar graph, using a what we call a time series graph with the line connecting each point, it allows us to focus more on the trend in the data rather than the relative size or area of the bars. And what's different here is that we see that there's actually a little bit of a decrease starting in 2010 that wasn't really shown when we had the bars before. Okay, here it looked like it stayed kind of constant, but because the population was actually growing there, the relative number was decreasing. I don't know if we necessarily want to present it that way, depending on the situation. Anyway, that's a larger question, not for statistics. Okay. So, notice again, we still use this kind of zigzag mark because we skip the first bit because all of them have that amount in common, and then we can then more kind of zoom in on this area where we see the bigger differences between the number and how specifically it has changed from one year to the next. Okay. Oh, there's a lot of glare there. Sorry. Actually, let me turn off this light. That's a little bit better. This is a 3D pie chart. Whenever we look at 3D data, it tends to not be great for a lot of reasons. In this case, because we're representing a 3D data from an angle on a 2D surface, being the book itself, it really has a lot of problems. And we look at this visually, And you say, okay, we're talking about educational attainment in the year 2013. Visually, it looks like these are the two biggest pie pieces right here, which is people that are not high school graduates or people that have graduate or professional degrees. Okay? And then we have bachelor's degrees, associate degrees, some college but no degree, and then just a high school diploma. Or not just a high school diploma, but a high school diploma. So, we kind of see the relative size of these, but there's no numbers on here that tell us what percent each pie piece represents, so it may not tell the whole story. If we look at a different view of that same graph, basically they took that graph and they rotated it in 3D. Now it looks like associate's degree is the biggest piece of the pie, and then what was up here, the not a high school student and not a graduate professional degree, those now look like the two smallest pieces. These two pieces here look like they were the two largest when they were in front. But when they rotate the graph and put them in the back, they look like the smallest. So what is the true story here? Well, if we look at the actual data, this is a nice 2D pie chart. We're not trying to... It's not as visually interesting, I'll give it that, but it accurately conveys the data that it represents. And so as long as we're trying to be true to the data and represent it properly, this is the ideal scenario because it doesn't skew how any of these pieces are viewed. And we see that in reality, the largest group is the ones that have high school diplomas. After that, we have our some college, or sorry, a bachelor's degree would be next, and then some college but no degree, and then not a high school graduate and graduate or professional degree are both tied, 12%, and then associate's degree is 10%. So this is kind of the ideal representation because we can see the different sizes in the pieces and see, okay, clearly this is the largest piece, this is the next largest, and so on. This is the smallest. When we have that 3D representation like we have over here, doesn't really tell the full story because of the distortion created by taking that 3D object and presenting it on a 2D surface from an angle. I mean, we look at it top down, but even if it's 3D, it's still just basically 2D. But ultimately, that's the best representation right here. So part of being a statistician is being responsible in how we present our data, especially when it's for formal research being presented for the sciences or sociology or something like that. Because our goal is to represent data, not to mislead. Now, this one's kind of the same thing. We have the soccer balls that represent participation in soccer. And we have 1991 versus 2009 here. Now, how are they presenting these? Let's see. They don't really tell us. Sorry. They actually give us the data here. There's 10 million participants in 1991 and 14 million in 2009. Now, would you look at this and say, okay, this is 10 million and this is 14 million? It looks like this soccer ball is many times larger than what was present in 1991. But we actually only increased from 10 million to 14 million participants in youth soccer leagues. So this is vastly misleading, whether they're using like the radius or something to that effect to represent the change. Or it's probably a situation where they just cut off the first X million and just showed growth from one to the next from there. But it really misleads the change in participation that we saw from 1991 to 2009, because it only increased by about 40%. This looks like it multiplied by 10 times maybe. So, again, not a great representation. All right. That's all I have for you today. I do need to... I lost my place, I'm sorry. I do need to assign you homework. I will post pictures of this in Canvas as usual. But I think we'll go with what I talked about already, which is that problem, I think it was 35. Zoom back out. Light back on. There we go. Oh, no, now you can't see it. Problem 35, and specifically, let's create, how many data values is this? Looks like 24. Yeah, so create like a stem and leaf chart, create a group frequency histogram with, let's say, 5 classes, and then create a group frequency distribution with 5 classes, and then create a histogram, and then comment on the shape of the distribution. Let me write that down. I'm keeping you all a little late, I'm sorry. I got carried away with graphical misrepresentations of data. Go ahead and look at 21 too. But yeah, on 35, we want a stem and leaf, group frequency distribution with 5 classes. A histogram for relative frequency, and a comment on the shape. Alright, so look at those, and we will continue this on Thursday. You all have a good rest of the day, and I'll talk to you all then. Take care, all.